Okay, let's conclude. Okay, I'll just copy from here to here. Okay, and the Laplace of G is minus delta R. Okay, and G is 1 of pi 4 pi R. There's a boundary condition which is very, very important. Okay, the boundary condition V is known, and these are imposed. I'm saying this is important because this is imposed, and this is given. Okay, I impose this just to write down. Okay, the Green's identity that I copy from there, I put over here. Okay, then I can say from this, I can say that the operator on V and the operator on G, they are self-adjoint. Okay, in general you call formally self-adjoint. Okay, there is a formally. Okay, now you see from there I know that the Laplace of V, I want V. Okay, that's what I want. Okay, the Laplace of V from the Poisson equation is minus rho divided by the permissibility. Okay, and I already obtained the Laplace of G. Okay, is minus delta R. Okay, now I substitute now G by 1 of 4 pi R. Okay, then I put I'll do this. Okay, I put here 1 of 5 pi rho. Oh, I'm sorry, epsilon 0. Now I'll plug G right here. Okay, look at it. Okay, this is integral on a volume. Okay, now this is look how it's quite easy. You see, this is minus. I'll put minus over here. Okay, now rho divided by epsilon, I'll put over here. So this is be rho PQS. Okay, that's a dummy variable. Okay, divided by R. Okay, this is G. Okay, already did here. Okay, is 1 over pi. This is I. You see, look, minus 1 of 4 pi R is G. Okay, I'll just put colors here just so you to see clearly. Okay, look, I'll put the same color. See the color of G here. This is R. This is 4 pi. Okay, 1 of 4 pi R. Okay, look at here. It is G. Okay, then the Laplace of V will be minus rho divided by epsilon. So I took care of this. Okay, now this is dV. Okay, so this is equal. Now I substitute here delta R. This is minus integral of V. Okay, attention now. This is V, the same V. I put it right here. Okay, now minus delta R dV. Attention now. Okay, I'll write down here V of R. Okay, I'll write here just. I do like that. V of R. Okay. Now delta R. Now dV. Okay. Let's separate here. Okay. Now the property. To remember the property that we did before, okay, delta R will activate R, okay, and set to 0, so this is equal minus V R is equal to 0. This integral is minus here, okay? I'll set, look at how interesting. Okay, I can erase here this minus and erase this minus over here. So this is plus, okay? Just multiply both sides by minus 1. Now it's ready, okay? This answer, okay? V at I is equal to 0. This is point O prime. This point O prime. That's what I want, is equal 1 4 pi epsilon 0, okay? Integral of the volume, this is rho PQS over R dV, okay? Yeah. I'll just do like that. This one is just this one here, okay? V R is equal to 0, okay? That's the property of the delta function, which is important, okay? Okay, now R, you see R over here, is the position vector of point Q minus the position vector of point O prime. That's a coordinate, the spherical coordinate R, okay? Now, what is important now? I'll make a very important point. Okay, you have, suppose, you have a differential equation, okay, linear, that I want to use the green function. Okay, if I impose on the green function the same boundary condition, okay, this highlight is the same for one variable, okay, no problem, one volume. The domain for it was one axis instead of a volume. Now, if I impose this, the operators, okay, they will be formally self-adjoint, and the G will be symmetric. The green function will be symmetric. Just to remind you that when you start studying green function, you have to remember that in the linear algebra, if a matrix is symmetric, okay, now there is some properties of symmetric matrix, okay, and similarly, if we are dealing with the self-adjoint, formally self-adjoint operator, G will be symmetric. Look how beautiful is this. You see, look, this is the equation over here is just this one, okay? I'll put it right here. This one is just this one, okay? Look, suppose this is my G, okay? My G over here. Now, suppose I want to check, okay, if G is symmetrical. So G is a function of P, Q, S, R, X, Y, and Z. X, Y, and Z. Now, it's symmetric, it will be G, X, Y, Z, P, Q, S. Symmetric. Let's see. Okay. You see, this square root, it is symmetric. Why? Because I have a square over here, okay? If I exchange X and P, Y and Q and Z and S, doesn't matter, I'll get the same result. Now, if I exchange the row, you see me, by X, Y, and Z, look, X, Y, and Z, okay? Instead of dP, dQ, ds, I will exchange P by X, Q by Y, and S by Z. I just have this volume over here. You see? Doesn't matter. But what is important now, these X, Y, and Z are dummy variables, okay? Dummy variables. And P, Q, S are the fixed variables. So these now represent point O prime, okay? And this X, Y, and Z represent point G, okay? Now, that's a dummy variable, okay? That's the G. The Q, I'm sorry. X, Y, and Z will be a point Q. You just exchange variable. The integral will be the same. It is the same since I assumed self-adjoint operator. Self-adjoint. That's the same thing, okay? I just transfer, okay, this here just to be more clear over here, okay? So that's my final result, okay? The solution of this equation is represented by the right-hand side, which the charge density, I know, the distribution, okay? And I want to find out the influence. Look, that's important. Look, you see, this is the volume, okay? This is my point O prime, and here's point Q, okay? Okay, this is continuous distribution of the charge, and how they influence the charge over here, okay? That's what I call rho at this point here. This point is equal to 0, okay? That's point O prime. You see, this is a continuous distribution. Okay, in general, in the electromagnetic problems, for instance, you have discrete charges, okay?